Okay, so here we go. Today is the first ever Dressler homemade recording, online video, and the topic of the day is going to be a little introduction to sequences. So, what is a sequence? Well, here's one that we started early on in the semester of a sequence, and that would be the following sequence: be 1, 5, 9, 13. I remember what this one is? Yeah, this is that when I assign every other odd problem, I would write something like this: 1, 5, 9, 13, indicating that's every fourth one. So this is a sequence. We give each one of these terms a name. A sub 1 equals, well, 1. A sub 2 equals 5. A sub 3 equals 9, and so on. 13, 17, etc., etc. Now this particular one you may have heard we call an arithmetic sequence. And the reason this is an arithmetic sequence is because it shares get out of there, has a common difference. So if I look at these terms here, 1 to 5, the difference is 4. 5 to 9, the difference is 4. 9 to 13, the difference is 4. So when I say, well, how do you describe the sequence? And you could say it implicitly, which might be the first one that comes to mind, if not, you may not call it implicit, but you might think, get out of there, that, where am I? That a sub n plus 1 is a sub n plus 4. All right, so what does this say? That the next one in the sequence is the previous one plus 4. So if I know that a sub n is 9, then I know a sub n plus 1 is going to be 13. Right? But then if I said, hey, what is a sub 306? Right, well, I don't know what that is, because I'd have to say, I'd have to start somewhere. So I could start with a sub 1 equals 1, and then I know a sub 2 would be 5, a sub 3 would be 9, etc., etc. So it might be more useful to us if we can define this one explicitly. And I could do that by saying that a sub n equals this a sub n. Oh, that's terrible. Let's erase that. So it's amazingly hard to have good handwriting with this thing. So I always complain to you guys about bad handwriting on your quizzes, and now here I am doing the same thing. A sub n equals, well, the way I think of it is 1 plus n minus 1 times 4. All right, so what does that mean? The first one, a sub 1 up here is 1. So a sub 1 equals 1 plus 1 minus 1 times 4, and that equals 1 plus 0 equals 1. Okay, so that works out. But another way to write this, you could write it as a sub n equals 4n minus 3. Right? Now, if you look at this, these two are, the two definitions, this one up here and this one down here, are algebraically the same. But this one actually is probably a little neater. But when I think of these things, I think of it this way, which is fine. You just have to shuffle it around to do some manipulation to get it to look right. So now if I said, okay, well, I need to know a sub 306, well, that becomes a lot easier to do now. So then 4 times 306 is 1224. So 1224 minus 1 equals 1220. Oh, sorry, that should be minus 3. Equals 1221. All right. So we can see here that an explicit definition of a sequence is a little more useful than an implicit one. All right, let's go over to the next page. And we've got to talk about something that I know Christine is looking forward to, and that's the topic of convergence. All right, and what does it really mean, convergence? What does this mean? So we've got a handy little definition that I swiped from the book. Let's put that in here, and we'll drag it up here. All right. Good enough. So definition is a sequence A sub n converges to the number L if for every positive number epsilon there corresponds an integer big N such that for a little n greater than big N, some stuff here implies that A sub n minus L is less than epsilon. If no such number, man, I mean, this is painful to read. I'm not even going to read the rest of it. Let's take a step back and say, what does this really mean? This sequence converges to the number L. So let's look at one like this. Let's say that A sub n equals 1 over n, right? We're pretty sure this converges to 0, right? The bigger n gets, the closer it gets to 0. So it converges to L, so we can assume, we think L equals 0. All right, so it converges to L. For every positive number epsilon, there corresponds an integer n such that all this stuff. Well, what is epsilon? Epsilon is really like a tolerance. So this is really a tolerance. So we're kind of after closeness to L. All right. And so if n is big enough, if the index is big enough, this little n down here, if this little n is big enough, if it's bigger than n, that the difference between A sub n and L, the difference of my nth term and this limit that I proposed is less than epsilon. So someone might say, all right, well, I want my epsilon to equal 1/500th. Right, so that's a challenge. That's like saying, I bet, or I'll believe that it converges if you can find some n that's so big that the difference between my nth term and L is less than epsilon. All right, well, then you say, okay, well, fine. N equals 501. All right. Then, you know what, a better way to write this? What if someone challenged you, I want to get it, this close, 2,000ths, right? And then you say n equals 501, and that means A sub n, or A sub 501 equals 1 over 501, and then so if we do our test here, 1/501th minus 0, so the distance up here between my nth term and my proposed limit is definitely going to be less than epsilon. All right, so this works out. Can I get really close? And no matter how small an epsilon we pick, can we find an n that's big enough that it works? Sure. Okay, so that is the definition of convergence. Christina, that's all for you. So let's charge ahead here. So there's a few rules. Page 553, theorem 1. So if you look at page 553, theorem 1, that look like this. So, well, I'm going to pause this and get this for you. Okay, so here I'm back, and we look at this. So I just wanted to get an image of this for you. What we're looking for is limit rules. This guy here. Okay. Come on, move, huh? So this is theorem 1. It's on page 553 in your book. Why is that not okay there? So, similar to what we did with other limits and then this differential operator, we know that the limit as n approaches infinity of a n plus bn is the same as the sum of the individual limits, right? The difference rule, goes right along with that if the sum of the if we have kind of a combined sequence here, we can say that the limits is the difference of the two individual limits. A constant multiple, we can pull a constant outside of the limit. So just pull the k out here and then find the limit of b sub n, and that works out here. Now here's one that is a little unusual in that the product rule, right? I can take the limit of the product of two sequences, and that's the same as the limit of the product of the two limits itself. Now that is different than the differential operator. It's different than the derivative. It's different than the integral. All right. So if I've got what looks like the product of two sequences, then the limit of that product is the product of the limits. Same deal with the quotients. All right. This doesn't work with derivatives or integrals, but it works with this. All right. So 1, 2, and 3 we're used to seeing. 4 and 5 are a little different. Now we've got a few more tools that we should look at. One is called the sandwich theorem, and it's kind of got a funny name, but what it's saying is if we have some sequences that the sequence B kind of falls between A and C, so B is in the middle here, A is smaller, C is bigger, and the limit of A sub n, limit as n approaches infinity of A sub n, is the same as the limit as n approaches infinity of C sub n, and they're the same limit, then the limit of the middle one of B sub n, now this is the middle one, also equals L. So if B is stuck in between A and C, and A and C are both converging on the same thing, that means B has got to converge on the same limit. All right, so that's if it's sandwiched in there. Another handy one that will come up is our old friend L'Hopital. And that says that if we have some limit such that, well, let's say the limit as, we'll say, n goes to infinity of f sub n over g sub n. So our sequences are really defined by some function, and that equals one of these indeterminate forms, 0 over 0 or infinity over infinity. It's got to be one of these two. It can't be any other indeterminate form. Then this limit as n approaches infinity of f of n over g of n equals the limit as n approaches infinity of f prime of n over g prime of n. Now it's very important, and I can't emphasize enough, it's got to be one of these two indeterminate forms. If it doesn't look exactly like this, you have to do some shuffling around to get it look like that. But we'll do some examples that look like that later. And that's Theorem 4 in page 555. You can take a look at that. So now let's put a little reference card in our toolbox, and let's look at some handy limits here. Okay, so this one is going to be really useful later on. So here's a bunch of handy limits. One is the natural log over n itself. Ln of n over n goes to 0. The nth root of n goes to 1. Some of these may look obvious. I'm not going to prove them right now. The proofs are all available in the appendices of this book. But for now, the rest of this lecture you'll take it on faith. The limit of 1 plus x over n to the n is e to the x. Okay, that's kind of an interesting one. The limit of x to the n over n factorial equals 0. All right, so that's kind of the factorial grows faster than this exponential case here. For any x, doesn't matter what x is. X could be really big, and factorial still grows faster. So that goes to 0. So this is a handy toolbox. We're going to come back and look at this guy a lot. But for now, let's take a look at some examples. So, example. So does this sequence a sub n equals 1 minus n cubed over, let's say, 70 minus 4n squared converge? All right, does this thing converge? Well, a couple different ways we could do this. We could plug an infinity over infinity into this thing, and we could say, well, this is going to grow faster than this. The infinity cubed is greater than infinity squared. So our guess is that it's not going to converge, but let's try to be a little bit formal about that. But this becomes infinity over infinity, so that implies that we could use L'Hopital here. And if we do that, we can say that the derivative of this, which is, let's see, negative 3n squared over negative, 8n. Well, that's still infinity over infinity, so let's keep going with this. That becomes, let's see, negative 6n over, that's just negative 8. All right, so now we're talking. So now it's 6n over 8. So that definitely goes to infinity. So the answer is it diverges. Right. Alternatively, we could say, let's say, other method. We could say, I'm going to factor out an n cubed. So I'm going to say this is n cubed times 1 over n cubed minus 1 over factoring n cubed out of the bottom. And no, I'm just going to factor an n squared out of the bottom because I can't get an n cubed out of there very handily. So this becomes 70 over n squared minus 4. All right, so does this do much good for me? I don't know. Let's keep going. The n cubed and the n squared cancel, leaving me just an n on top. And this becomes, let's see, 1 over n cubed minus 1 over this thing here, 70 over n cubed minus 4. All right, well, I don't know. I don't know if I made any progress. But we know we've got these difference and quotient rules, so we'll apply our difference and quotient rules. And so 1 over n, did this work out here? Yeah, this works out. 1 over n cubed, right? This part here definitely goes to 0. No doubt about that. Minus 1, so this goes to minus 1. So we're looking at n goes to infinity. So this goes to infinity times minus 1 over, this definitely goes to 0. This definitely goes to negative 4 then on the bottom. So it's 1/4 of infinity. Well, 1/4 of infinity is still infinity. So here, yeah, that's not a very good one. Let's give you a new infinity sign here. So 1/4 of infinity is still infinity, so this one diverges. Okay. So a couple different ways you can do it. Either one is legit, as long as all the individual steps are legit. So let's take another look at another example. How about this one? Does a sub n equal the natural log of n over the natural log of 2n? Does this thing converge? Well, we look at this thing, natural log of n is infinity. Natural log of 2n is, well, that's infinity too. Those both get big really fast. So let's apply L'Hopital here. Again, Lo. I'm not sure what that little caret does, but I think it's important. L'Hopital. So the derivative of natural log of n is just 1 over, natural log is 1 over n. And the derivative of natural log of 2n is 1 over 2n, but you have to multiply by this in a chain rule, so it's 2 over 2n, which equals 1 over n times 2n over 2. Well, look at that, the n's cancel. Oh, you know what I'm going to do? I'm going to get crazy here, guys. I'm going to get rid of that canceling. And check this out. So I'm going to say the n's cancel different color, huh? And go back to black here. So we're left with 2 over 2, which equals 1. Oh, so that's interesting. That will converge. That converges to 1. Now, you might have looked at this part here and said, okay, this here and this here, that goes 0, that goes to 0. So 0 over 0 is indeterminate, and so you apply the chain rule or the L'Hopital again and apply it again and again. Whereas if you do a little shuffling around, you can get straight to the answer of 1 there. All right, so I think that's an important one to note. So let's do another example here. How about a sub n equals 1 minus 1 over n to the n. Now, this one is not at all obvious. So when we get these not at all obvious ones, what do we do? Well, let's go back here. So it's that looks kind of like this. Yeah, I'm not sure. Let's take a look. So we know we've got this 1 plus x over n to the n. But here we have 1 minus 1 over n to the n. Boy, I don't know. Can we use it? Well, I think I can rewrite this, kind of like I do with my differential equations. I'm going to rewrite this so it looks exactly like what I need. 1 plus negative 1 over n to the n. All right, let's check. Does that look the same? Where am I here? I lose my pointer a lot. Yep, too far. So 1 plus 1 over n to the n, or x over n to the n, equals e to the x. So when I go back to this guy, 1 plus negative 1 over n to the n, that's going to equal e to the negative 1, which equals 1 over e. Good, so that one converges. It looks a little bit like one of our tools that we've got. Let's see, do I have room on this next one? I'm going to go to the next page for the next one here. Right? We got plenty of paper. It's not even paper, it's electronic paper, so we're just burning electrons. How about this one? Does a to the n, n factorial, so we know factorials grow pretty fast, over 2 to the n, 3 to the n. Right? What about that one? Well, 2 to the n times 3 to the n, that seems kind of silly to me. So let's write that as n factorial over 6 to the n. Does that look like anything else? So we have n factorial over 6 to the n. So we've got to go back down here, take a look at our rules. So where's our rules here? We've got that natural log one, this one. Oh, here we go. X to the n over n factorial. X to the n over n factorial goes to 0. Right? So we got to remember that the factorial grows faster than the exponential. X to the n over n factorial goes to 0. Well, now I don't remember what our thing looked like. So the exponential over the factorial goes to 0. So we have to page forward here. Ooh, no, this doesn't work out. So are we screwed? No. Let's rewrite this as 1 over, how about that, huh? Then I can write it as 6 to the n over n factorial. Now it's the same, right? But I know for my limit that equals 1 over 0, right? Now I know what that is. That's infinity. So that diverges. Right, so here the key thing is we had to do a little algebraic manipulation in order to get it to look the way we want. All right, let's do one more. Yeah, I think I've got, yeah, just one more. And then it's done. Then you guys are real experts. So does a to the n equals n times 1 minus cosine of 1 over n, does that converge? Well, as n gets really big, so we have to kind of look at this thing from the inside out. So, as n gets big, that that goes to infinity. And then 1 minus cosine of 1 over n. 1 over n goes to 0. The cosine of 0 is 1. So this equals infinity times 0. Now this is definitely indeterminate, right? That's one of those forms I spoon-fed you that one on a quiz a few weeks ago. Infinity times 0 is indeterminate, but we can't use L'Hopital. Yeah, there's not much we can do with it. So how do I rewrite this? Well, n, much like on that quiz problem, I could rewrite this equals 1 minus cosine of 1 over n over 1 over n. Right? Now, how does that going to work out for us? 1 minus, okay, so we know that this goes to 0. Cosine of 0 is 1. Cosine of 0 is 1. 1 minus 1, 1 minus 1 becomes 0 over 0. Well, so we took this indeterminate form with which we cannot use L'Hopital, and now we can. So we can use our old friend L'Hopital again. I like L'Hopital, so I'll put exclamation points. So we take the derivative of, so cosine of 1 over n, what'll that be, is sine of, let's see, 1 minus, so it'll be the sine of 1 over n, right? Derivative of cosine is negative sine, so that's actually a plus. No, but this goes away. You know what? We're going to start this over. When I take the derivative of the 1, that goes away. The derivative of cosine is negative sine, so that becomes negative cosine becomes a positive sine of 1 over n. But the derivative, then chain rule says we have to take the derivative of 1 over n, which becomes negative 1 over n squared. And the bottom, the derivative of 1 over n becomes negative 1 over n squared. So the sine of 0 is, because 1 over n will go to, this goes to 0, the sine of 0 is 0 times 0 over 0. So that's, did we make any progress? But I think we did, because we can go back up here and in red, because I really like canceling stuff out in red. So I can cancel this 1 over n squared with this 1 over n squared, and I'm left with this thing equals just the sine of 0, which equals 0. So this will in fact converge. Alright, so that's all I've got for you. A few examples. The homework is pretty long. There's a lot of them. Don't spend more. I'm going to write that. This is important. Don't spend more than, let's say, 5 minutes per problem. Right? Because we'll do some group work tomorrow, and if you're stuck on one, then maybe somebody else did it. Exclamation point. You know what? Let's go. Oh, check this out. I'm going to go thick red. Don't spend a lot of time. Then when we're doing the group work, you guys can save yourself and work together. So you got stuck on one, you got stuck on the other, and let's call the whole thing off. All right. Thanks, guys. So I've got to get out of here, pause my recording. I'll see you tomorrow.